Okay, so it's time to start. So our second speaker this morning is Evgeny Gorsky from UC Davis, and he will speak on Hecke category and Hilbert scheme.
All right, thank you. So I'd like to thank the organizers for inviting me, and I'd like to thank Pavel and Andrei for teaching us lots of beautiful mathematics. So I was preparing for this talk, and I think if I would have met Pavel and Andrei, I would have known zero things that I'm going to talk about. So zero mathematical notions, zero objects. So I think 10 years ago, I had no idea of any of this. Whatever. So thank you for teaching me all this. So my motivation comes from invariance of knots, which is kind of separate from what I'm going to talk, but I'll say something. So basic observation is that if you have braids on n strands, mod skein relation, and skein relation means that I have a piece of a braid like this minus a piece of a braid like this, q minus q inverse, like this. And so this thing is nothing but the Hecke algebra, more or less by definition. And we can also take closed braids on n strands, mod skein relation. And by closed braid, I mean that I take a braid with some number of strands, I close it up, but I close it up in the annulus. So I have a hole here. I'm not allowed to move strands through this hole. And so in particular, I'm not allowed to change the number of strands. And so this thing, again, more or less tautologically, is either the Hecke algebra mod the commutator, so the cocenter, or by a result of many people, it is naturally isomorphic to the ring of to the space of symmetric functions. Of degree n. And there are many proofs of this. And there is a natural map which takes a braid here and closes it up. And let's call it trace. And so again, it's nice in many ways. In particular, it visualizes many symmetric functions. You can draw them as closures of some braids. And so the goal of today's talk is to categorify this. And so more precisely, the conjecture that we posed with Andrei Negut and Jake Rasmussen a while ago So what is categorification of Hecke algebra? So I'll say more precisely in a minute, but it is some kind of Hecke category. And we want some kind of trace map to something which categorifies degree n symmetric functions. And my favorite categorification is the derived category of coherent shifts in the Hilbert scheme. And so we expect some kind of functor like this. And I want to list just three properties. So first of all, it is a trace. So I lower star of xy is I lower star of yx. The second property is that I can take homes in both categories, but I want to take home from identity to x in the left-hand side. And then this is actually the same as home from identity, which is the structure shift, to I lower star of x. And this is nothing but the homology of the Hilbert scheme with this object I lower star of x, or hypercohomology if this is a complex of shift. And so in particular, you can compute homes on the left-hand side using homes on the right-hand side, or vice versa. And then the third property that I want is that I lower star commutes with the action of some natural operator, the full twist. So if I have x times the full twist, this is just I lower star of x, tensor with of 1. So this is a line bundle on the Hilbert scheme, and the full twist is a braid which is nice and central and so on. So I didn't say what it is, like what is an object here labeled by a braid, but if we think of it as a categorification of this picture, there should be an object for each braid, and that is what I mean here. And so the conjecture is that there is a functor of these categories satisfying these three properties. And so what is known, so there are at least three approaches to this, which are all very different and all conjecturally equivalent. X is an object in the Hecke category, which I didn't define. Yes. So here, X and Y are in the Hecke category. And I'll specify it in a second. I just want to do it in this generality. And so the approaches. So there are three of them. So the first is due to Oblomkov and Rozansky. So they are very brave and very bold, I would say. They just defined a new version of Hecke category using Hilbert's scheme of points. And lots of other things. So I won't say anything about this, but Alexei, I think, will say. So see Alexei's lectures tomorrow. Right? He will say it tomorrow. Okay, whatever. So now he is forced to say it tomorrow. Whatever. So this, I won't say anything about this, but in their setup, somehow, this is really closely related to the Hilbert scheme, and then this functor is more or less built into the construction, although you still need to prove all this ABC. So a different approach uses essentially just B and C. So that I will explain again everything. So project to full twist. So basically it says that B and C determine I lower star uniquely. And I will explain this in detail. And then the third approach is what is called categorical trace. This is newer. So I don't want to categorify this or that. Instead, I want to use A to say what does it mean to have a category where objects are closed braids. So you just use A and define a category generated where objects are closed.
So this condition B, it's so these conditions, do they imply that this functor is fully faithful or no?
No, it's not. It's much smaller. I mean, it's like the trace, so you forget a lot of information. So the Hecke algebra is bigger than the symmetric functions.
But for from 1, it is.
Yes.
So 1 goes to O.
Yeah, secretly it's some kind of projection formula. So secretly I won't say this, but there is another functor, and pull back of O is 1. And then this is just the projection formula for this. Okay. I think I will.
I star of 1 is O.
I lower star of 1. No, it's not O.
So what does I lower star?
I lower star of 1 is purchasing. But I'll say this later. I lower star of 1 is purchasing. Okay, I want to keep this, I guess. I don't know what I want to keep. Let's see. All right, so now what version of Hecke? So I will talk about 2 and 3. I need to define the Hecke category now properly, and I will use Zorgelbay modules. So I use ring R, just polynomials and n variables, and then I use, so I have an action of Sn on this thing, and I define BI to be R tensor R, or invariance under transposition. So this is R bimodule. And then, by definition, S beam N is the smallest subcategory of RR bimod containing R, BI, and closed under direct sum, tensor products, direct sums, and direct sum ends. And so this is the category of Zorgil bimodules. And so the fundamental theorem of Zorgil is that this is the codification of the Hecke algebra, meaning that split graded Grotny group of this category is the Hecke algebra. And so the split means that I consider only direct sums. And then, in particular, Q in the Hecke algebra corresponds to the grading shift. So all these bimodules are graded, everything is graded, and so there is a natural notion of Q here. And so this version is more algebraic and more easy to deal with by various reasons. In particular, it has this grading. But for many purposes, it's equivalent to other versions of Hecke category that other people like perverse shifts and flag varieties and other things. But again, this grading and just the algebraic structure of this will be crucial for me here. Okay? And so, well, this is Hecke algebra, so BI don't correspond to any braids. To braids, we get different things. So there are objects Ti, which are complexes. And Ti inverse. So these are complexes of Zorgil bimodules. And the theorem of Roquet is that Ti and Ti inverse satisfy braid relations up to homotopy. So I didn't say this, but because we work with bimodules, you can tensor them, and we have tensor product here, and so you can tensor this thing, and this corresponds to multiplication of braids. And so as a corollary, so if I have beta is any braid, so I can associate T of beta is a complex of Zorgil bimodules, well-defined up to homotopy. And so, again, it won't be so important for me later, but because I mentioned all these braids and braid invariants, so remark, so hom from identity to T of beta. So I have this complex of Zorgil bimodules. Identity is just the R. Maybe I should say this. And then I can take hom in this category. And then this is known as Kavanov-Rosansky homology. And so, in particular, this is a topological invariant of the link. Okay? So this is the version of Hecke category. It's not Zergel bimodules, but it's complexes of Zergel bimodules up to homotopy. So let me measure this down. So our version of Hecke cat homotopy category of SB band. And it's not the same as derived category, but let's ignore this issue. Okay, and so now here is some concrete theorem that we proved with Matt Hogenkamp. So for all k greater than 0, we can take home from in this category from identity to full twist to the k. So recall that full twist is the braid like this. And for this braid, by this construction, I can associate a giant complex of Zergel bimodules, and I can take home. And then this home is isomorphic to I to the k mod y I to the k, where I inside polynomials in x1, xn, y1, yn is the ideal generated by anti-symmetric. Should I switch marker? Polynomials. So what's written here? So you take polynomials in two n variables. You have an action of Sn on this thing, which simultaneously permutes x's and y's. You can take ideal generated by antisymmetric polynomials. Let's call it I. So this is a module over x's and y's. And take k's power of this ideal, and then kill maximal ideal in y's. So this y is y1, yn. And so this is still a module over x's. We killed y's, but it's still a module over x's. And so the claim is that this is isomorphic. So this is true as our modules. So agrees with our module structure. So on everything that you get from this construction, you have a natural action of R. You take our bimodule, home is still our bimodule, but it's actually our module. And it agrees, so the action of R here and the action of R here agrees. And also it agrees with multiplication, which is more important. So you have multiplication from home, from identity full twist to the k. Full twist to the L, and it goes to home from identity to full twist k plus L. So you have natural multiplication here. You can tensor multiply homes, and here you can multiply things. So I to the k times I to the L embeds into I to the k plus L. Right, and maybe I want to say, just for sake of clarity, so all these things are graded, and so homological grading. So I don't keep track. Change the pen again. So xi is better? Huh? Yes? Have homological degree 0, and yi have homological degree 2. So it's not true that this giant complex has homology only in degree 0. It has lots of homology, but it's actually like this. In particular, all homology is supported in even degrees, because everything that you can get here is in even degrees. So maybe I'll write it as a special part that all, so homology of hom 1 to ftk is supported in even homological degrees. Okay. So I don't think I have time to say anything about the proof, but I want to give an example to just give some flavor of how this looks like.
Do you know what happens to negative?
We do, yes. Yes, we do. Because full twist is the Serre-Fanter. But the answer later. Yeah, so there is some description, but it's less explicit in some sense. Right, so example, for n is equal to 2, we have just one crossing, which corresponds to the complex from B to R. And then full twist is 2 crossings. So this is B to R tensor B to R. And then you can check, so it's an exercise, that this is a 3-term complex which looks like B to B to R. So hom from identity to B is hom from identity to R is R. And so hom from identity to full twist is again a 3-term complex. Now we replace each of these guys by hom from identity to the corresponding bimodal. So this will be R to R to R. So this map is actually 0, and this map is actually x1 minus x2. And so you can see that homology of this complex is concentrated in degrees 0 and 2. And it's a nice exercise to check that it matches with this I. So in this case, I is in C of x1, x2, y1, y2. And this is just generated by x1 minus x2, y1 minus y2. And you can check that I mod yi actually matches this description. But it's non-trivial, and homology is in every even homological degree in some sense. Okay? Any questions? No questions? Good. And so why do we care? So first of all, where is the Hilbert scheme? So I programmed this Hilbert scheme, and there was some ideals and things. So you have Hilbert scheme of endpoints on C2. And I forgot to mention, so this ideal I is very closely related to ideal J that Eric defined yesterday, but it's really closely related to what I'm going to say. So it's really closely related to what Eric was explaining. So Hilbert of C2, it is a resolution of singularities of symmetric power of C2, and you have a natural map from C2 to the n, which projects to Sn of C2. And then there is this object xn, which is the fiber product, or more precisely, reduced fiber product. So this is called the isospectral Hilbert scheme. And so let's call this P. And so an important theorem of Heyman describes all this pretty explicitly. So in particular, xn in this projection is just the blow up of C2 to the n along the union of all diagonals. And then this ideal I that appeared on the previous board is nothing but the ideal defining this union of diagonals. Let's call this delta. And so more generally, this xn is proj of I to the k. That's more or less what is said to be blow up. And so, in particular, another thing which is important is that I to the k is free over C of y1 yn over half of the variables. And so in particular, we had I to the k mod y I to the k. So if you take proj this is nothing but this is P inverse of y1 yn is equal to 0. So take this fiber product and then you take pre-image of the half space where all y coordinates are equal to 0. So it's inside X.
Can you read that last line to me again? Part of what?
So you have this ideal I to the k.
Yeah.
Then you take I to the k mod y I to the k. You still have graded algebra structure on this thing. So you have, maybe I should put brackets around this. So this is a module over x variables, and you can multiply these things for different k. And this is still a graded algebra. You take proj, and that is by definition pre-image of the half space in here.
Change the crayon again. Change the
You know, it has to do with overall quality of markers.
Let's try black. Sorry. All right, and so the construction is better. For now, it's better, at least, yes. So we have any x. So it was x and xn, but that's fine. So let's call beta to be a braid. So beta is a braid, or it is an object in SBMet. And then we can associate to it the direct sum over all k homes from 1 to beta times raised to the k. So this is a graded module over direct sum of k form of 1 to t to the k. So this is a graded algebra, and then more or less tautologically, this is the same as the coherent sheaf on proj. Of direct sum to the k. Yeah. I mean, part B and C are more or less the same as A. Yeah. I mean, the follow from A, or how to say. I mean, this is non-trivial part in some sense. That the ideal I that I was writing is the ideal defined in these diagonals. But once you know this and this, then C is automatic. That's right. And so this is the same as proj, okay, of this direct sum of ik on yik. And we just defined what it is. So this is this p inverse y is equal to 0. And so we get a sheaf on this thing or on some subvariety of this thing, and then we can just push forward of this sheaf. So here we just apply push forward, and we get a sheaf on Hilbert. So that's the construction. It works nicely on the level of homology. Again, if you the reason the conjecture is still a conjecture is that you have to be really, really careful with derived categories and all this. But at least it's very constructive and very explicit, and you see how the Hilbert scheme appears naturally. And so answering Pavel's question, so if you start from identity object here, then you get this algebra as a module over itself. You get all of this subvariety, and you push forward to get Procesi or Procesian Lagrangian. So Procesi bundle, maybe I should say this, so push forward of all xn is P is the Procesi bundle that Eric again defined yesterday. Okay. And also, so the fact about full twist that I said, that if you add a full twist to beta, then you switch by O of 1, it's again automatic from this construction. Because if you add a full twist, you just shift k here, you shift k here. And again, by definition of proj, you tensor with O of 1. That's again all tautological.
Well, I apologize. I didn't somehow. Whatever you're going to get from this construction is supporting some subvariety.
Yes.
You're going to get O.
You don't get O. I mean, here you'll get Procesi on Lagrangian subvariety. So if you want the whole thing, then you need to add y's, and that's a separate story. But somehow, yeah, maybe I should say this as a statement, that in particular, so example, so if you start from identity, then you get O on this preimage of y is equal to 0, and then by push forward, it will get Procesi restricted to Hilbert n of C to C. So these are sheaves supported on a line y is equal to 0. But again, everything is flat over y, so it's not such a loss, and you can actually insert y in the picture, but I won't talk about this. Okay? So this is basically this construction.
That was your, you had this kind of yization of Zirkel.
Yes. So this yification of Zirkel bimodules insert y's in this construction, precisely. So, but let me save time and not talk about this. Okay, so this is the second construction, which is basically, again, what it says is that if we want this functor, if we want some kind of algebraic variety, maybe Hilbert scheme, maybe something else, and we want this property that home from 1 agrees with this I lower star, and action of the full twist agrees with O of 1, then tautologically it should be proj of this algebra, and then you just need to compute this proj of the algebra, and that's what it over there. Okay, and so the third part is newer and more familiar to many people here, but less comfortable for me in some sense. So let's see how this goes. So we can forget about all this. And so the third idea is the derived traces. So suppose that, so again, so the goal is to define category where objects are closed brace. some sense. And so it will be actually a DG category. And so more generally, if I have C, a monoidal category, I can imagine another category which is called horizontal trace.
That's not readable.
HTR.
No, it needs to be doctorate. Is there something like that? My eyes are sort of.
Yeah, I'm sorry.
Not as good. That's good.
That's better?
Yeah.
Every time it's done in your mind, it's better.
Yeah, before 2 minutes.
No, when you
Use dark markers.
Okay. So this is, let's go derived horizontal trace. And so this is really DG category. And so the objects are the same as the object of C. And the morphisms are complicated, and I won't define them. So they use some kind of bar complex and all that stuff. So I will give you one example of morphisms in a second. And so the properties are that, first of all, there is a trace functor which goes from C to H tur of C. And tur of xy so is tur of yx. So this is, in some sense, it's universal trace functor. And then another property, which is more understandable, is that you have a distinguished object here is identity, and you can take trace of identity over there. And so you can take endomorphisms in this Htur of trace of identity. And then, or of identity if you so this trace functor just send, because the objects are the same, it sends the object to the object with the same name. But let's distinguish them and put trace of identity. And so the endomorphism is Hochschild homology of the original category C. Yes.
So you have an isomorphism. What sort of?
There are quasi-isomorphisms. So there are homotopy equivalent in this. So.
Okay, so you don't require higher coherence. You just have coexistences you have to.
I mean, this is built in somehow. This is built in the construction. Like how you define this isomorphism and do you have higher homotopies, that's a separate issue. But somehow these objects are isomorphic. So you have a natural morphism in this trace from here to here. You have a morphism back. And the compositions both ways are homotopy equivalent to identity. Right, and so I was saying that, so there is a general notion of Hochschild homology of a category. In general, it's just a vector space, but if your category is monoidal, it's an algebra. And so this algebra structure here agrees with the composition of morphisms over here. And in general, like you can imagine complex computing this, and then the version of home is some kind of version of this complex. And I don't want to define any of this. So this is some black magic. And I have to say, while erasing that, of course, many people considered some other versions of this, like Benzin Nadler and Lurie, I guess, and other people, but they're so smart that I don't understand anything they do. So it's easier to redefine this more concretely. Right. And so now, in our case, C is SBMN, or homotopy category of that. And so a theorem that we proved with Matt and Paul Vedrich is that first of all, Cauchy homology of S beam n is isomorphic to polynomials in n even variables, which are all our x's. Then you have exterior algebra in n variables, so these are odd. And then you have semi-direct product with Sn. And so remark is that for He0 was computed before by Lice and Lauda by different method. More importantly, so there is some complex compute in this homology, and there is some complex compute in this then. And so this is actually formal as DG algebra. And so the third thing is that actually the trace of identity in type A, but we're all in type A. So term of identity generates, or say split generates, this category which is Hecke. And so the picture that at least I have in mind is that, so what is identity? Identity braid is something like this. Then you want this category where the objects are closed braids, so you close them up. And now trace of identity is really n circles encircling this hole. And now, for example, it's clear that you have a send action on this thing. So Cauchy homology of this category is endomorphism of this object. So this is ter of 1, and its endomorphism of this is this complicated algebra. But in particular, it's obvious that you should have a send because you can permute these circles once you close them up. You cannot permute them before you close because somehow these points are fixed. But once you close them up, you can permute them, and you have this ascend component. And then this is really just the Cauchy homology of R. So that's morally what's going on here. And now the fact is that, so you have this ascend action here, so you have a lot of idempotents, and then you take all direct summands of this guy, and they really generate the category. So i.e. direct summands of ter of 1 generate. And so maybe I want to say one comment about the proof because it's actually so easy that I can explain. It's much easier. So this theorem, like all this setup of DG categories and things and complicated stuff, it looks much more complicated than just computing home from identity to default width. But actually, computational-wise, this is much easier to prove. And the key tool is that, so the key idea in the proof is that homotopy category of S beam has the same orthogonal decomposition where these are complexes for positive leaves of braid, positive leaves of permutation. Positive braid leaves of permutations. And so in the morphism, in the original category of TW is just R, because it's invertible. And there is a theorem of Kuznetsov that I want to cite here, which says that if you have a semi-orthogonal decomposition, then you have a direct sum. So Hochschild homology of semi-orthogonal decomposition is a direct sum of Hochschild homology of cements. And so in particular, in this case, we have Hochschild homology of my category. It's just a direct sum of roll W, Hochschild homology of endomorphism of TW. And so this is direct sum of roll W, Hochschild homology of R. And that's what it is here. And this doesn't give you the algebra structure, and it doesn't give you formality, so you need to work here. But again, using grading and other tricks, you can actually do this.
Is this theorem like saying that if you have two traces of a triangular matrix, then you don't care about what is above diagonal?
Yeah, more or less.
Okay.
Yeah.
Categorical version.
Categorical version of this, yes, I guess. Okay, so now some comments, and yeah, so this is completely separate. And I'd like to, in 2 minutes, I'd like to convince you that many of you actually seen this statement. And the reason you've seen this statement is that this horizontal trace of SBMN should be more or less related to the category of character shifts, Lustics, which also appeared yesterday. And so there was a lot of work in this direction, again, in much more abstract way that I can digest, unfortunately. So in particular, Ben-Zvi and Nadler gave some precise statement along this line. And in some sense, dual statement was worked out by Bezrukavnikov, Finkelberg, and Ostrich. So we are talking about the cocenter. They were talking about Drinfeld center, which is in some sense dual. And so what is going on here? What does this picture represent? This picture represents the Springer sheaf as a character sheaf. So if you like sheaves, that's what it is. And then in the morphism of Springer sheaf, like classically, you don't have this part, but you have this part and this part. The formality was proved by several people, like in particular by Laura Ryder, in this setting, again using some kind of grading argument. And then the fact that trace of one split generates the category means that some ends of the Springer sheaf generate the category of character sheaves in type A because we're in type A. So this is some kind of derived version of what's going on here. And you have the status, and you have to be slightly more careful with formality. But again, like for most people here who like sheaves, unlike me, this should be actually much easier to digest. Huh? I mean, right side has no differential.
No,
I mean. Oh, no, I don't understand what they proved. No, they have geometric construction. So they work with geometric version of the Hecke algebra. Maybe I should say Hecke category. So you have geometric version of Hecke category as some kind of sheaves on the flag variety, and there is some kind of infinity category way of defining a trace. And then, again, this machine, which I don't understand, spits out character shifts tautologically. And so again, like, I don't understand what's going on there, to be honest. And so I'm not sure the digit structure and formality you can get as easy as you can get it here.
If you know formality on
let's talk about this later. So I don't know. I mean, this is just a comment, which again, I'm not fully understand this work. Okay? I don't know what to say wrong. Okay. So what I said I want to say is that in principle, like again, where is the Hilbert scheme? So we had the first approach, and there was a question, where is the Hilbert scheme? We have the second approach, and where is the Hilbert scheme? And so recall that we have this xn by pi to Hilbert, and we have this guy Precesi, which is push forward of Oxn, and then a theorem of Bridgeland, King, Reed, and also by Heyman, I guess. Is that first of all, in the morphism of P is now polynomials in x1, xn, y1, yn, semi-direct product Sn, and then again P split generates dbq of Hilbert C2. I hope you can read it. And so there is a clear analogy between this and that. Formality is also, I mean, it's not a question here.
What does it mean, split generate?
So the summand. So again, you have an action of Sn here. You take all direct summands with all that important in the group algebra. The summands of P generate. So you have an action of Sn. In group algebra of Sn, you have lots of idempotents. So they give you summands of P. And summands of P generate. It's exactly the same story as over there. And so the hope and the conjecture is that there is some kind of Cazul duality which goes from here to here, which sends x's to x's and thetas to y's. And so the conjecture is that there should be some Cazul duality. But that's a big question mark and still work in progress.
What does this mean?
Huh?
I mean, definitely the algebra suffers from Hilbert in some sense.
Yes.
I don't see a statement.
The statement is that you can go from this category. So you have DG category with these properties. And you have some kind of functor from this category to this category.
So your horizontal trace category.
Yes, yes, yes. So the conjecture is that there is a functor from the horizontal trace to derived category of Hilbert. Because we said that there is a trace-like functor from the original category to Hilbert. If it is a universal trace, then it's better factor through a horizontal trace.
So these algebras are Cazul dual, and the conjecture is...
I mean, they're Cazul dual over X, which is additional
Right.
problem.
And the conjecture is that this duality leads to a level of chains. Is that what you want?
Yes, 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 yes. So the conjecture, let me write it, is that there is functor from the to the derived category of Hilbert, which realizes this Cazul duality. And I have to say that using this geometric picture, there is a very different approach by Kostya Tolmachov, where he geometrically tries to construct this functor. And so this is related. So I think I'll stop here.
Are there any questions? Comments? May I ask you a question?
Yes.
So, what happens, what replaces Hilbert scheme will replace type A like type D?
Yeah, that's a very good question. So this statement works in any type, and formality works in any type. The generation doesn't work because Springer shift just doesn't generate. So this breaks down, and I don't know what's going on here. The previous theorem, where you compute Holmes to the full twist, it's also very much type A thing. But you can ask if there is some version of this for other types. Nothing is proven, but like natural candidate, for example, is that, so here you have C2 to the n blown up along diagonals. there you take Cartan plus Cartan dual and blow up along codimension 2 things where you have root hyperplane and dual root hyperplane. So you have this codimension 2 things in Cartan cross Cartan dual, you blow up, you get something. It's normal variety, very singular. And so that might play a role in this picture, and that might be related to this homology of the full twist. It's related to some other interesting things, but that's just a guess. Let's see. And I don't know if there is a version of the Hilbert scheme, like any of this. Yeah.
But for type B, maybe there is some. Well, type A.
Yeah.
Type A.
More questions? Okay, so let us end this picture again. And we will do one further, which is earlier than yesterday. Sorry? 15 minutes ago.
Yeah.